Hello, my name is Eric Hernandez, and today I want to talk to you about a very interesting problem in statics, which it's often presented in one way, and then the solution becomes fairly elementary. But when presented in another way, it's not that easy to solve, and it actually requires some interesting geometrical trigonometric formulas. Specifically, we're going to use Heron's formula to solve this problem. So let's start. The typical problem that we encounter in most statics textbooks is the problem of given a force such as this one here pointing down, which we're going to call P, and given two other forces, which we're going to call F1 and F2, and usually what we are given is the direction of these two angles, theta 1 and theta 2. So given P, theta 1 and theta 2, find F1 and F2. So that problem is elementary. We can solve it using simple formulas from statics, just postulating the equilibrium in x and y, right? So if we say sum of forces in x, sum of forces in y, we can easily find F1 and F2, right? If we sum of forces in x, we have minus F1 times the cosine of theta 1 plus F2 cosine of theta 2 equals to 0. And if we think in the vertical direction, then we have minus P plus F1 sine of theta 1 plus F2 sine of theta 2 equal 0. And anyone that has taken a course in statics can solve these two linear equations, which are simultaneous linear equations, but there is really nothing to it. However, there is another way to look at the problem which makes it a little bit more challenging. Let's say that you are given P, F1, and F2. But you are asked to find the angles theta 1 and theta 2. Now that problem is a little bit more complicated, right? Because if you go back to these equations, now you see that theta 1 and theta 2 are nonlinear functions, right? They are sines and cosines, and those functions are nonlinear. So now you have two equations with two unknowns, but the equations are nonlinear. And so it's not clear how to go ahead and find those, right? So how can we do this? Well, we can solve this problem if we use a formula that comes to us from Heron of Alexandria. And the formula goes like this. If you want to find the area of a triangle, and so let's say the triangle has sides A, B, C, and you wish to find the area, let's call it AT, of that triangle, but you don't know the angles. You just know that this triangle has these three sides. How do you find that? Well, the formula goes something like this. AT is given by the square root of S minus A times S minus B times S minus C, where S is the semi-perimeter of the triangle, which is the sum of all the sides divided by 2. Basically, that's the formula. So how does this formula relate to this problem here that we wish to solve? Well, the way that it relates to it, as you can already begin to see, is that we basically are equilibrating these three forces. Well, three forces are in equilibrium if they form a closed triangle. So then we go back to this triangle and we think of each of them as a side of the triangle. And now the missing piece is how do we connect this Heron's formula to the equilibrium? Well, and specifically about finding the angles theta 1 and theta 2. So it turns out there is another trigonometric identity that goes something like this. If this is this triangle, right, and these angles, so we call the angles opposite to the side by their capital letters, right? So then this here becomes angle A because it's opposite to side A, angle B opposite to side B, and angle C, capital C, opposite to side lowercase c. So there is a very interesting formula that goes like this. The sine of the angle A is equal to 2 divided by side B times side C times the area of the triangle given by Heron's formula. So, if you know the sides, you can find the area, and that area comes in here, multiplies by 2 divided by BC, and that gives you the angle of A. The angle of A is the angle between side B and C. So you get to choose what side you want to call A, B, and C, but eventually the angle A will be given by this formula right here. And you can verify this very quickly by doing any simple example. So let's say that we are given, just to put numbers to this, so let's try to solve an actual problem by using this formula. So let's say that I have three forces and they are equal to the following values. I'm going to omit the units just for simplicity. Let's say P is 200 in consistent units, F1 is 175, and F2 is 100. And I know these forces are in equilibrium, I just don't know at what angle are they in equilibrium. So the first step is that I'm going to find my value of AT, right? So AT, and before I find that, I have to find the semi-perimeter. And so I'm going to do that. And if I do that, we find that the semi-perimeter is equal to 237.5 in this case, because the perimeter is the sum of 200 plus 175 plus 100, which comes out to 475. So half of that is 237.5. And then we simply plug that into Heron's formula, and we find the area of the triangle being equal to 8,748.6. That's AT. And then we go to this formula and find the sine of the angle. So sine of A, we mean the angle between B and C, is going to be equal to 2 times AT, which is 8,748.6, divided by B times C, 200 times 175. So since we have selected 200 and 175 as B and C, the angle A that we're going to find is the angle between those two, right? And because of the properties of the sine, we're going to find not this angle right here, but this one actually right here. And when you do the calculations, the angle A comes out to actually 29.99 degrees. Now, how do we find the other angles? Well, the other angles, we can find them by the law of sines. Very simply, right? If you remember law of sines, it says that sine of A divided by A equals sine of B divided by B, sine of C divided by C. So if we use this formula, we can quickly find the angle C, which is the angle between A and B, right? Which is the angle between these two right here, right? That's B and this would be A, right? In our case. And so by doing that, we obtain that the angle C is equal to 61.04 degrees. And basically that gives us the setup that achieves equilibrium, right? 99.99 degrees, and this one 61.04 degrees. So if you put those forces with those angles, they will equilibrate this force right here. And you can verify that by just plugging into the equations of equilibrium, right? And it will all work out. So again, a very interesting application of Heron's formula, right here, right? And statics. I think that's very, very cool.